Okay, this is lesson 5.3b. So we're going to start talking about tree diagrams. So I'm not sure if you've seen these before, but anytime this process is like multi-stage, it's a great way to represent it. It's a good visual way. It really helps us just figure out the probabilities. So this is what a tree diagram looks like. In this case, the sample space are all the possibilities of randomly choosing a school day and noting if Shannon hits the snooze button or not, whether or not she gets to her first class on time. So the first tree branch there is, does she hit the snooze or not? The second branch is, does she get to school on time or not? Evidently, she has a problem getting to school on time, but you can see, at least seems to be, when she doesn't hit the snooze, she gets to school 90% of the time on time, if that's the case. So it does seem like it's probably good to not hit the snooze, I guess. But that's what a tree diagram does, and we can go more into it in a minute. So recently, Harris poll reported that 20% of millennials, 25% of Gen Xers, and 21% of baby boomers, and 17% of matures, which are old folks, read more ebooks than print books. According to the U.S. Census Bureau, 34% of those 18 and over are millennials, 22% are Gen Xers, 30% are baby boomers, and 14% are matures. Suppose we select one adult at random and record which generation person is from and whether he or she reads ebooks or print books. So I guess the first thing you have to decide, and this is probably like when you're getting started, the toughest thing, like, is my first branch going to be the print or ebooks, or is it going to be which generation you're from? Is it going to be like millennials and so forth? So the key that maybe if you read closely here, it said 20% of millennials read ebooks, 25% of Gen Xers. So my first thought is, let's make the first branch what classification you're in, and the second one whether you read ebooks or print books. So if I were making this, what I would do, now I'm going to get my pen out. So it said, if I look at this, so it says 34% of those 18 over are millennials. So 34%. So 34%. So 0.34 is how we write that, are millennials. 22% are Gen Xers. Gen X are 22%. 30% are baby boomers. 0.3 are baby boomers. And I believe it was 0.14. 0.14 are what we call matures. I haven't heard that term before. Okay, so by the way, if you add those up, what should happen if you add up 0.34 and 0.22 and 0.3 and 0.14, it should be 100%, right? You're one of those generations if you're an adult, basically, is what they're saying. So now let's go further to the second branch. So it says 20% of millennials read ebooks. So 20%, so 0.2 read the ebook. Which means by default 0.8 must read the print book. And you keep going with this. And so 25% of Gen Xers, 25% of Gen X, so 0.25 read the ebook, which means 0.75 must be the print book. I'm just going to put a P there. 22% of Gen Xers, no, sorry, 21% of baby boomers, 21%, so 0.21 are ebooks, which means 0.79 are print. And finally, the matures, 17% of matures, so 0.17, which means 0.83 are print. Okay, So the thing that I want to show you that they didn't do, but I think you should do here, is the last step, which is to kind of summarize. So to get this, so you want to multiply to figure out the probability of those two things happening, 0.34 and 0.2, being a millennial who reads ebooks or prefers ebooks. So you're going to multiply 0.34 times 0.32. So 0.34 times 0.2 is 0.068. So 0.068. To get this one right here, you're going to do 0.34 times 0.8. So 0.34 times 0.8 is how you get to that branch. So 0.34 times 0.8, 0.272, 0.272. For this one, you're going to do 0.22 times 0.25 to figure out what's at the end of this one. That's the probability of that branch, both those branches happening. So 0.22 times 0.25, 0.22 times 0.25. I'm going to go and do the next one, 0.22 times 0.75, 0.055. And 0.165. Okay, this one is 0.3 times 0.21 would be the end of this branch, and we're going to do both of those as well. 0.3 times 0.21, then 0.3 times 0.79, so 0.063, 0.063, and 0.237, 0.237. And let's do the last two. So we're doing this times this to get this one. So 0.14 times 0.17, 0.14 times 0.17, and then 0.14 times 0.3. So 0.0238 and 0.1162. Now, if you added up all those numbers at the end, so the 0.068 plus the 0.272 plus 0.055 plus 0.165, all those numbers up, if you add them up, it shouldn't surprise you, those are going to add up to 100%. So now we have the probability of each one of those things happening. Like, what's the chance that you are in the mature group and you prefer print? That's 11.65%, right? So what's the chance that you are in the Gen X group and you prefer ebooks? That's 5.5%. So you can figure out the probabilities of each of those, the likelihood of each of those things happening. So I usually do this at the end. I know it takes a little time there. You'll do it a little faster when you're not doing a screencast and do it on there and going back and forth, but definitely just fill them all out. You never know which questions they're going to ask and what you're going to need for that. So I would just go ahead and do that. It's going to make it easier. They didn't do that. You notice they did theirs without filling out the ends, the likelihood of each thing happening by multiplying those two things. And I think that's a mistake. I think you go ahead and just do the ends of it. Figure out the probability of each because you're going to use it in just a minute anyway. So find the probability that a person reads more ebooks than print books. So now you're looking at more ebooks. So we have to add up all the probabilities of ebooks, right? So you see there's 4 different cases of ebooks there. So the top case, millennial ebook, then Gen X ebook, then baby boomer ebook. So you're adding up all those numbers. So if you went back to our thing, so you'd add up this, whoops, that was print. You're adding up this 0.068, you're adding up the ebook for 0.055, the 0.063, and the 0.0238. So we've already figured those out. We just have to add those up. They haven't figured it out yet, so they're going to have to multiply those numbers, the green ones, and then the multiply purple and add them, and so forth, and do that. That's what they did here. It's kind of hard to read, but they did the green ones. They multiplied them to get the 0.068. That's what we had. The purple ones, the Gen Xer, multiply those to get 0.055. Add up all of those together to get 20.98%. So there's a 20.98% that you prefer ebooks rather than print books, just in general, no matter what group you belong to. Suppose the chosen person reads more ebooks than print books. What's the probability that he or she is a millennial? So we know that 20.98% prefer ebooks. So we already have half this answer, right? Our denominator is going to be 20.98% or 0.2098. Now we need to find out what proportion of those are millennials. We already figured that out when we did the 0.34 times 0.2, which was 0.068. So that's our numerator there. And you get, 32.41%. Multiplication rule for independent events. So this is the derivation, I think, essentially of that formula. So the formula I know it as is just probability of A times probability of B. You're just multiplying it. If event A and B are independent, then A having occurred or been given is not going to affect B at all. So you're literally just multiplying these two probabilities together here. And that's how I would say it. That's how I learned it. You just multiply probability of the first event times the probability of the second event. It's a very easy formula to use for independent events. That's when the events don't have any effect on each other. This applies only to independent events. That's absolutely true. Okay. Many people who visit clinics to be tested for HIV, the virus that causes AIDS, don't come back to learn their test results. Clinics now use rapid HIV tests. Oh, that's interesting. Give a result while the client waits. In a clinic in Malawi, for example, the use of rapid tests increased the percentage of clients who learned their test results from 69% to over 99%. The trade-off for fast results is that the rapid tests are less accurate than slower laboratory tests. Applied to people who have no HIV antibodies. One rapid test has a probability of 0.004 of producing a false positive. There's always a problem with tests. There's always some false positives. Falsely indicating the antibodies are present. If a clinic tests 200 randomly selected people who are free of HIV antibodies, what is probably that at least one false positive will occur? Assume the test results for different individuals are independent. So the probability of no false positives would be, so that's saying that you get no false positives. So if there's a 0.004 chance of being a false positive, the chance of no false positive would be, for all 200 tests, you're going to do 0.996 to the 200th power, essentially there, which is what they're saying, which is evidently, if you type in your calculator, 0.4486. So the chance of no false positives at all would be 44.86% of the test for all 200 tests. So if there's 200 folks, there's most likely going to be a false positive. Probably at least one false positive would be the complement of that event. So at least one means that, if 44% of the time there's no false positives, then the other times, there's going to be at least one. So you do the complement of that event. So 55% of the time, oh my goodness, 55% of the time you're getting at least one false positive. This is awful, right? So even though that 0.004, very rarely does it give you false positive. If there's 200 tests, you're going to be wrong on, probably at least one of them, So keep that in mind. That's going to happen. So in 2015, Spotify revealed 47% of its users are aged 13 through 24. Wow. Got to be young to be using Spotify. 25% are 25 to 34, and 28% are 35 or older. I didn't even break it down any further than that. Suppose that for the 13 to 24-year-olds, 85% identified pop as their favorite music genre. 59% of 25 to 34-year-olds identified pop. And then 23% of the old folks identified pop. So I hope you kind of see which one the first branch is there. Because it says, so first we're going to branch it out by age group. Then if they like pop music or not, or don't have pop as their top. So when you do it, you want to definitely break it out by age group first, do that, and then break it out by pop, because they kind of identified that. Said of the 13 to 24-year-olds, 85% identified pop. So music. So that's how you would do it. So that's the hard part, I think, is identifying what's the first branch there. Then we have a tree diagram. Of course, I want you to go a step further. Go ahead and just get the ends of the branches. So for that first branch, the young folks, you multiply 0.47 times the pop, which is 0.85 in that case, and get your decimal and write it off to the right there. Do that for all 6 of those possibilities. Because you're going to use some of those, it might just be helpful to go ahead and do that all at once. The question is, find the probability the person identifies his or her favorite music as pop. So in this case, we would have to do what? We would have to multiply 0.47 times 0.85. That's the young folks who like pop music. And then the medium age folks, 0.25 times 0.59. And then the old folks, 0.28 times 0.23. If you add up those 3 terms, so that plus that plus that, you get 61.14% of folks like pop music. Okay, and so you would use that. Suppose the person identifies his or her favorite music group genre as pop. Okay, so out of those folks, out of those 61%, what's probably that is age 13 through 24? So to get this, again, we already figured out the 13 through 24 was, I believe, the 0.47 times 0.85, that one. So that divided by the 61%, which is pop, that should be our answer. So it should be 65%, I believe. Let's see what they got. So yeah, you add those up to get 61.14%. And then you take that answer of the pop for the young folks divided by the pop for everybody, and you get the 0.6534. In 2012 interview with CBS News, Tom Hanks said that 80% of the population are really great, caring people who help you and tell the truth. And I think 20% of the population are crooks and liars. A new lie detector suit has been tested and shown to correctly identify truthful people 88.9% of the time, and correctly identify liars 75.6% of the time. Evidently, those tests are not foolproof. Those are not good percentages there. I don't think it could be used in a court of law. A positive test is one in which the person is identified as a liar, and a negative test is one in which the person is identified as truthful. Sometimes the test suggests that a truthful person is a liar, false positive. Other times the test indicates a liar is being truthful, a false negative. So assume that Tom Hanks and the company make a lie detector suit are telling the truth. So assume Tom is right, 80% of folks are truthful. A random selected person from the population tests positive for being a liar. Find the probability that the person is a liar. So actually is a liar if they test positive. So testing positive doesn't mean you're necessarily a liar, but what's the probability that that person would be a liar? So we've got to figure out the first branch here. So it seems like, I guess the first branch would be, let me just think this out. So 80% are truthful, 20% are not truthful. So then of the 80% who are truthful, you would then break it out into, test positive or test truthful, so to speak, is 88.9, which means, 1 minus 88.9 or 1 minus 0.889 would be the liars. And so you draw your, so the 80% truthful, so a negative test, So negative is one in which a person identifies truthful. Oh, I had to read that. So negative test identifies as truthful. So if you really are truthful, so 0.80% are truthful, and then you also test negative, because that's considered truthful, would be 0.889 there. So I had to reread that the way they wrote that. Okay. So you get your tree diagram. I would figure out all 4 of those probabilities at the end. Just use your calculator and multiply through on each one. And it says, let's see the question. A randomly selected person from the population tests positive for being a liar. Find the probability that person is a liar. So test positive. So now we have to figure out 2 of those things, right? So we're going to figure out those 2 guys, add them up. And so we added up those 2 things to that would be our denominator, right? So we do the 0.8 times 0.111 and 0.2 times 0.756. And so we get the denominator is 0.240 there, but we want the probability that the person is a liar and has a positive test. So correctly identifies as a liar, I guess here. So it would be 0.2 times 0.756. And so the probability of that happening would be 0.63 when you do that all together. Okay, so 63, find the probability the person is a liar. 63% of the time, that would be true. Wow, these are terrible false positives, false negatives. These are not good there with that one. Multiplication rule for independent events. So Mrs. Johnson decides her AP Stats class gives a pop quiz with 4 multiple choice questions. Each multiple choice question has 5 possible answer choices. John did not do the homework or do any studying, so he uses the rand_int function on his calculator to guess on all 4 questions. What's the probability that John guesses correctly on all 4? So there are 5 possible answer choices, right? So are those events independent? So the question is, does the first guess have any effect on the second guess? I would say no, right? They're totally independent, right? So if that's the case, you just multiply the 4 different possibilities. It'd be 1 out of 5 times 1 out of 5 times 1 out of 5 times 1 out of 5. Or 0.2 times 0.2 times 0.2 times 0.2, which is 0.0016. Yeah, so 0.16% of the time, less than 1% of the time, he's going to get all 4 questions right. That is not a great percentage there. Maybe you should study. I think that's the lesson you can learn from that. In the United States, 28% of the population has hair that is blonde. A couple in the United States is expecting quadruplets. Does this mean that there is a 0.28 times 0.28 times 0.28 times 0.28 probability that the quadruplets will all have hair that is blonde? So are those events independent? So if 28% of folks are blonde, and some couple, we don't know if they have blonde hair or not, is expecting quadruplets, is color of hair independent of each other for each kid you have? Does it matter what color hair your parents have? And I think it does. So I think these are not independent events, so you cannot do it that way. Because each child's hair color is not independent of the hair colors of other children. Certainly your parents' genes would have something to do with the traits that were inherited there. So, I don't know exactly how that works, but I know that it's definitely not independent events there. Great, that's your lesson for today.